able to be there in person. So yeah, in this talk, I'd like to discuss some of our recent works towards leveraging foundation models to boost the performance of physical AI systems, along with strategies to ensure their safe deployment, with a focus on autonomous vehicles.
Sorry, Professor Michael. We need to show you some. Let me show it. Yeah, that works.
Can I continue?
Yes, we can hear you.
All right, yeah. So, yeah, the premise of this talk is that the foundation models provide the key opportunities to accelerate the development of physical AI systems, such as autonomous vehicles. And to be more specific, by foundation model, I mean a model that has been trained on broad data, typically at internet scale and a self-supervised fashion, and they can then be adapted to a wide range of downstream tasks. Example foundation models include large language models, vision language models, and video generation models. Now, we're not quite yet at the level of one massive model that can consume any data modality and be adapted to any application, but the general approach of pre-training on diverse data at massive scale and then the fine-tuning has proven extremely useful for numerous downstream applications, as many of you have likely already experienced. Now, the question is, how can we access this generalist source of knowledge for AV applications? And the answer is in multiple ways. Unique foundation models can empower several aspects of AV design and development, from improving offline development processes such as auto labeling, simulation, and scenario generation, all the way to drastically improving driving performance, either by enabling novel, more performance driving architectures or by enhancing driver assistance systems. In other words, foundation models provide opportunities to empower the full AV program. So in this talk, I'll focus on how foundation models can significantly advance the capabilities of onboard AV stacks, and in turn, how such a powerful AI-driven stacks can be confidently deployed in the real world. Now, as mentioned at the beginning, foundation models hold the promise to allow us to drive better through more generalizable decision making. But then the question is, do we actually have evidence for that? And we've recently explored this question through our work, Agent Driver, and confirmed that there is potential. Specifically, our work, Agent Driver, treats large language models as embodied agents that loosely replicate how humans drive. That is, leveraging capabilities on demand like detection and prediction, cognitive memory, chain of thought reasoning, and so on and so forth. And these different modules are orchestrated by the large language model through text as a unifying interface, calling the different modules on demand. And remarkably, this rather straightforward embodied pipeline enables few-shot decision making, which achieves a state-of-the-art performance. On the right, we can see that a model trained with only 1% of the training data surpasses the previous state-of-the-art model at the time, namely UniAD, trained on 100% of AV-specific data. And here the idea is that the large language model is capable of bringing in generalist knowledge acquired at internet scale pre-training to the task of driving, thereby only requiring a fraction of AV-specific data as compared to state-of-the-art academic models. So this motivates us to explore best ways to integrate foundation models into a fully fledged AV stack. And to systematically explore the huge design space, in a paper that we presented at the CDPR last year, we proposed a computational graph framework to model the general task of driving. And given this framework, we can reason about the different architectural choices. For example, in terms of which modules to use, how such modules should be arranged, and how information should be represented from latent features all the way to interpretable outputs. And I'm quite excited about this work as it provides one of the very first tools to systematically explore the design space for AV architectures and robotics architectures more broadly. So thanks to this framework, we were able to conduct extensive experiments among many different possible architectural choices. And our key observation is interesting and also somewhat surprising. It turns out that one of the simplest designs, namely a fully parallelized AV architecture, appears to be the best one in terms of both performance and efficiency. Briefly, this architecture, dubbed ParaDrive, entails a transformer that takes multi-camera images as input and produces outputs in parallel for four core AV tasks, namely mapping, motion prediction, occupancy prediction, and motion planning. Importantly, ParaDrive follows the principle of train heavy and infer light. In offline training, all parallel heads are necessary and crucial as the co-training of the different heads ensures that the learned features implicitly encode mapping, prediction, and other A/B capabilities, which then yields strong planning performance. Online, one only needs to activate the motion planning head for driving. In head-to-head comparisons with the state-of-the-art academic models, we show that this architecture runs faster, so about 4 times faster, while improving on performance. And equally importantly, this architecture retains introspection and interpretability options, as the auxiliary heads could be potentially exercised, perhaps at a lower frequency, to gain insights into the inner workings of the model, thereby also enabling runtime monitoring signals. So encouraged by these preliminary results, we further extended this archetype with three core lessons from the design of foundation models, namely the use of scalable self-supervised losses, such as next video and language token prediction, a tokens in, tokens out autoregressive transformer backbone, which itself can be trained from scratch or can be a pre-trained large language model or vision language model, and the use of internet pre-trained foundation models for tokenization. To evaluate this foundation model empowered design, we implemented a version of the model that uses a video generation as an auxiliary training loss and an autoregressive transformer backbone trained from scratch. And to assess performance, we can leverage a neural reconstruction to conduct a closed loop evaluation. Specifically, we use an in-house photorealistic sensor simulator to assess the value of this AV architecture. And in this video, we can see the model executing an unprotected left turn, for example, in general a challenging scenario for AV systems. Most importantly, we were able to achieve this performance in a fraction of the time and resources that would be required to develop this capability in a classical AV stack. So after gaining confidence in the model's closed-loop performance, we then deployed it on a vehicle. And on the right is a video showing the model reliably driving in the real world, specifically on public roads around NVIDIA's headquarters in Santa Clara, demonstrating behaviors including lane keeping, lead vehicle following, lane changing, smooth natural driving. And a model similar to this one is now being productized as part of the NVIDIA AV product. So going one step further, we experimented with using an internet pre-trained vision language model as the core autoregressive backbone. And immediately we see improvements in trajectory generation performance, with a pre-trained large language model backbone achieving lower trajectory error compared to the exact same architecture trained from scratch, and converging faster. Specifically, the blue curve here portrays the performance of a language pre-trained backbone versus the performance of a non-language pre-trained backbone depicted in the green. The x-axis represents the number of epochs for training purposes. The y-axis represents one of the metrics we use to judge model performance, with the lower, the better. So interestingly, this indicates that language pre-training synergizes well with the task of driving, corroborating our earlier results from agent driver. So we also conducted closed loop evaluations of this language pre-trained model. And in addition to driving reasonably in a variety of scenarios, as we see here, we found that it could also handle rare scenarios such as construction sites, which otherwise could give trouble to classical and end-to-end AV stacks trained from scratch on driving-only data. So it is quite evident that language-based capabilities improved performance. So how can we further extend this paradigm? Well, particularly to those with a control theory background, several goals should be readily apparent, including adding constraints and guardrails, more explicit accounting of uncertainty, inducing notions of Bible-like stability, that is making sure the system doesn't go crazy, and more explicit accounting of closed-loop performance requirements. Fortunately, there are several directions that are ripe for investigation and can collectively help us with addressing these goals, from more sophisticated policy structuring, as well as closed-loop training strategies, all the way to so-called test time intelligence, which is what I'd like to briefly discuss next. So that is recently, with the rise of reasoning models, we have witnessed a shift from training time to test time intelligence, whereby the models are endowed with an element of planning. These models have demonstrated superior performance to humans on various benchmarks involving complex, multi-step inference tasks. At NVIDIA, we had developed Cosmos Reason 1 as well as a smaller 1.5 billion parameter reasoning model. So why does this matter for autonomous vehicles? Well, driving is fundamentally a reasoning problem. The model constantly has to ask, what would the pedestrian do? What if I wait? What if I go now? And so on and so forth. A language-based reasoning lets the model explore multiple what-if branches before choosing an action. So that means that the model can consider multiple counterfactual scenarios. We can gain better online interpretability, and we can see why a model made a given decision, and we can unlock new monitoring signals to keep the AI in check. However, AV reasoning isn't just standard LLM reasoning. It has to integrate visual inputs, spatial dynamics, and of course, physics. So it also has to reason quickly, and any mistake could be dangerous. That makes it a unique and much harder challenge. So how do we imbue reasoning in our AV models? Well, instead of treating reasoning as a pure NLP problem, we focus on the unique aspects of driving. First of all, driving happens in a highly structured environment. So rather than reasoning in free form, we guide the model's chain of thought over such physics-based structure. And we produce reasoning outputs at two levels, detail reasoning traces primarily for training and debugging, and compressed meta actions for efficient runtime use. To obtain this kind of data at scale that can be used for further training, we need to carefully design a reasoning auto-labeling pipeline, which is quite complex. It's not just about tagging bounding boxes or trajectories. We need to generate interpretable, grounded explanations of what's happening in a driving scenario, similar to how an expert driver would think through it. And to handle the complexity, we break the pipeline down into multiple stages. In the first stage, we use rule-based methods to generate initial meta actions. Think of meta actions as actions such as stay in lane, change lane, yield to a pedestrian, and so on and so forth. Next, we bring in large vision language models. These models analyze visual frames to identify critical objects, understand the scene dynamics, and describe why a particular decision should be made. This step is crucial for grounding reasoning in visual context. It provides initial reasoning traces. Then we pass all this information into a large reasoning model, something like DeepSeek R1 or NVIDIA reasoning, which leverages a visual, vector, and ego motion context. And this model produces the final guided chain of thought reasoning traces, step-by-step textual explanations that lead to policy-ready meta actions. Here, an example that walks through the full chain of thought reasoning process. The system first analyzes the surrounding environment and identifies critical objects, which might influence the ego vehicle's decision making. In this case, there is a vehicle cutting in ahead. Then the pipeline will enter the reasoning phase and generate a guided chain of thought explanation. Finally, based on the reasoning, it outputs structured policy-ready meta-actions, in this case, decelerate, wait, and accelerate. With this high-quality chain of thought data, we can fine-tune our vision language action model. And here, in this plot, we show the performance of the vision language action model on a challenging long tail scenario benchmark comprised of about 300 manually selected clips with complex motion behaviors and auto distribution visual context. As can be seen, the addition of meta action supervision reduces trajectory displacement errors, one of the metrics we use to judge model performance, by about 20%. Supervising with the model's chain of thought reasoning traces further improves performance, reducing errors nearly in-house compared to the baseline vision language action model with only trajectory supervision. So this is a fairly exciting result that shows the potential of using reasoning models, particularly to handle complex auto-distribution situations. And we plan to release a comprehensive report of our findings on this topic later this summer. So stay tuned. Now, rightly so, there are a lot of concerns in the community about the use of foundation models in safety-critical applications, for example, due to their notorious occasional hallucinations. And while these are certainly valid concerns, it's important to recognize that foundation models are not black magic. They are fundamentally data-driven models, albeit large ones, for which we have several tools to keep them in check. These tools can be viewed as guardrails across the design phase, runtime deployment phase, and validation phase. Design time guardrails are steps we take in the design and training of foundation model-based stacks to ensure, for example, that they learn safe behaviors from the training data. In turn, runtime guardrails act as another layer of assurance, injecting sources of trust and diversity in the AV stack, for example, through runtime monitors that constantly check the health of the AI modules. And finally, validation and verification guardrails, which entail checking that the model meets rigorously defined safety KPIs both on real-world data and in simulation. Now, of course, safety is not a linear process, and while the material shown in the previous slide was shown in a sequential fashion, building a safe AV product is really an iterative process. Accordingly, the notion of a safety data flywheel is key behind the development of safe physical AI. And excitedly, several of our research results on the topic of AI safety have now been integrated within NVIDIA Halos. As announced at the last GTC conference by the NVIDIA CEO, Jensen Huang, Halos is a comprehensive safety system for physical AI safety, for which I'm fortunate to serve as tech lead. I could talk at length about each of the safety elements behind Halos. And indeed, here is a link to a half-day workshop we held at the last GTC on this topic. But what I want to focus on here in the last part of this talk is how foundation models have indeed the potential to improve overall AV safety, an aspect that to some extent has been largely overlooked so far. Those familiar with the safety engineering V model, we recognize two key aspects of building safe systems: the design phase and the validation phase. The common sense reasoning capabilities of foundation models provide opportunities to aid both aspects. On the design side, foundation models can become part of a safer AV system by serving as effective runtime monitors for key AI components. On the validation side, foundation models can be used, for example, to auto-label operational design domains from the raw data, measure the safety of a given behavior, and aid in generating safety-critical scenarios for testing, thereby creating a data flywheel for safety, as I mentioned before. Now, in particular, on the validation side, we have explored how foundation models can boost our existing capabilities for generating stress testing scenarios. Specifically, we have explored how large language models can enable an intuitive interface to controlling the generation of simulation scenarios. With our work, LCT Gen, we are able to not only control the initialization, but also the evolution of the simulation scenario via natural language descriptions. Uh, Briefly, LCT Gen works by first converting a given scenario prompt into a structured representation. And this representation is then taken as input into a map retrieval framework that selects the best fitting road layout from a dataset of maps. And the same structured representation is also used as an input into a motion generator, which places agents on the map and forecasts their motion for the next few seconds. Crucially, with this framework, we can seamlessly use outside sources of information, such as text-based crash reports, to generate a plausible scenes, the stress test AV stacks, with scenarios extracted from real accidents, thereby enabling a notion of plausibility in the scenario generation pipeline. And here are a few examples where we reproduce real-world accidents described in the NHTSA Siren database. In turn, foundation models can also enable more sophisticated runtime monitors to detect anomalies and trigger contingency plans. For example, I typically like to show the example of a video from a Tesla display that at first glance makes no sense. There are traffic lights that are spawned by a truck, but here you see that indeed there is a truck that is transporting traffic light that is confusing the AI on board of the Tesla. And here there is another example, this time of a stop sign on a billboard causing trouble. The interesting thing about these cases is that at the object level, you can't really say that, for example, the detector is functioning. I refer to this class of problems as semantic anomalies, that is, edge cases unseen in training data caused by the unusual and tricky combination of in-distribution objects. The semantic anomalies induce system-level autonomy failures, and while it may be difficult for system designers to foresee all of these cases, the key idea is that a little bit of additional contextual understanding is all that an autonomous vehicle would need in order to detect them. Accordingly, we have explored the use of foundation models, such as vision language models, to act as runtime monitors and decide upon the possible execution of contingency plans, with very promising results as reported in the below references. Recently, we have extended our semantic anomaly detectors to support both high-level and fine-grained physical reasoning, and I have applied these detectors to a variety of robotic application domains beyond autonomous vehicles. For example, hazard identification in construction robotics, runtime monitoring of marine autonomy, and also in space robotics applications. And if you're interested in auto distribution problems in robotics, we have a survey paper that provides an overview of this class of problems and some possible promising interactions for future work. All right, so I'll conclude it here by saying that foundation models really provide a quantum leap in long-tail generalization because essentially they provide us with a tool to leverage the generalist knowledge, internet-scale generalist knowledge, and bring it to our desired task, driving in this presentation. Importantly, foundation models have the potential to empower the full AV program, from offline processes all the way to the online AV stack. In the context of onboard performance, we saw how foundation models can boost the onboard stack in multiple ways, from improved tokenization methods to backbone pre-training, all the way to scalable supervision. And the recent shift toward test-time intelligence represents a promising new paradigm for physical AI, and in driving context, a very promising paradigm, particularly to address highly unusual situations, like, for example, complicated construction zones. Finally, safety is key, especially as we use these powerful models in the loop. We do have several strategies to indeed confidently deploy these state-of-the-art stacks. But at the same time, a point that I wanted to make is how foundation models actually provide opportunities to improve the safety of autonomous vehicles. For example, with better ways to generate stress testing scenarios or by enabling much more powerful runtime monitors. So I'll conclude it here. Of course, I will thank all my collaborators at Stanford and NVIDIA, and I'll be happy to answer any questions you might have.
Testing, 1, 2, 3.
Okay.
Okay.
So,
Any questions from audience?
Yes. So my question is about runtime monitoring. So large language models have the quite high latency. So what is large language model handling the runtime monitoring in this case? Because
Sorry, to repeat question again. So my question is about runtime monitoring using the vision language models. They are quite complicated in the sense that they are very high latency. So how runtime monitoring is happening? Is it on a spot happening or is happening some offline computation?
Yeah, this is an excellent question. So a runtime monitor is an additional algorithmic pipeline. So you want this pipeline to be as lightweight as possible from the point of view of latency. And you're right that the full autoregressive generation might be exceedingly slow, especially because you want this runtime monitor to constantly monitor the behavior of the system. So what we do in a paper that actually was presented at RSS last year is to disentangle the problem of anomaly detection from that of reasoning about contingency plans. For anomaly detection, what we do is to reason in terms of large language model embeddings, which is much faster. Actually, we show that we can do that at the level of milliseconds, and at the same time, allow us to still use the knowledge that is incorporated in the large language models. Then, if an anomaly is detected, then we slow down to buy ourselves a little bit of time to query a full-blown large language model to reason about contingency plans. Similar a little bit to how a human drives. So I like to think that you constantly have an anomaly detector in your head that runs very quickly and you don't even pay attention to. But when an alarm is triggered, then you slow down a little bit to buy yourself some time to really think about what's happening. So all of this to say that there are actually ways by judicially using large language models for monitoring to do it in real time on modern hardware. But you have to be a little bit careful. And if you're interested, feel free to email me and I'll send you a paper on this regard.
okay. Professor Michael Pavone, can you hear us?
Yes, I also see
Oh.
Brian there. Hey, Brian.
Hi, how you doing?
Very nice seeing you.
Okay. So due to interest of time, so we only ask this question, one question, and we will go to another speaker, Dr. Brian Ichter. Yeah.